Dear students, in the last class, we have derived the wireless estimators beta 1 hat and beta 2 hat. And as we have derived in the last class, beta 2 hat is equal to n into sigma xi yi minus sigma xi into sigma yi divided by n into sigma xi square minus sigma xi the whole square. And we have written it as equal to sigma xi minus x bar into yi minus y bar divided by sigma xi minus x bar square. That is sigma xi yi by sigma xi square. By sigma xi square. Now let us see how we have derived this equation from this. We can derive this from this or this from this. We consider two expansions, and these two expansions will be extensively used throughout our econometric course. The first expansion that we consider is the expansion of sigma xi minus x bar into yi minus y bar. This can be written as sigma of xi yi minus xi y bar minus x bar yi minus plus x bar y bar. xi yi xi y bar x bar yi x bar y bar. Taking the summation inside, sigma xi yi minus y bar into sigma xi minus x bar into sigma yi plus n into x bar y bar from the properties of the summation operator. Now, we know that these terms are equal. If we assume that we multiply a term with n, divide with n, so it becomes, expansion becomes sigma xi yi minus y bar into sigma xi. Can also be written as sigma xi yi minus n into x bar y bar. N into x bar y bar. A second expression for sigma x minus x bar into y minus y bar. The third expression is, now consider this equation sigma xi yi minus y bar into sigma x. This y bar is sigma y by n. So taking this n as LCM, we have n into sigma xi yi minus sigma xi into sigma yi. That is the third expression. N into sigma xi yi minus sigma xi into sigma yi divided by n. We will use these three expressions interchangeably later when we proceed. So these are the expressions for sigma xi minus x bar into yi minus y bar. Now consider the expansion sigma xi minus x bar square. This is sigma xi minus x bar into xi minus x bar. So that this can be written as sigma of xi square minus xi into x bar minus x bar into xi plus x bar square. Taking summation inside, sigma xi square minus x bar into sigma xi minus x bar into sigma xi plus n into x bar square using the properties of the summation operator. Now, these two terms will cancel because these expressions are same. So, one expansion is sigma xi square minus x bar into sigma xi. The second expansion is sigma xi square minus n into x bar square. Assuming that multiplying with an n and dividing with an n into x bar square. Also from this expression, taking n common, we can write n into sigma xi square minus n into sigma xi square minus sigma xi the whole square. So these are the three expressions for the expansion sigma xi minus x bar square. Now as you can see, in the numerator for beta 2 hat, what you see is n into sigma xi yi minus sigma xi into sigma yi by n. The expansion for this, you divided this with the denominator n into sigma x square minus sigma x the whole square by n, and n will be cancelled from the numerator and also the denominator, and you will get sigma xi minus, you will get n into sigma xi yi minus sigma xi into sigma yi divided by n into sigma xi square minus sigma xi the whole square. So this is beta 2 hat in terms of original observations on x and y. This is beta 2 hat in deviation form. As we have written in the last class, this can also be written as sigma xi yi by sigma xi square. Sigma xi yi by sigma xi square. And remember these two expansions always. Now, and beta 1 hat in deviation form is simply, beta 1 hat in deviation form is simply y bar minus beta 2 hat x bar. Y bar minus beta 2 hat x bar. So, keep in mind all these equations. Now there is one more easy method to derive the expressions for this beta 1 hat and beta 2 hat. Let me just introduce what are they. We have written the normal equations as sigma yi summum n into beta 1 hat plus beta 2 hat sigma xi. And second normal equation is sigma yi xi is equal to beta 1 hat sigma xi plus beta 2 hat sigma xi square. Dividing the first normal equation throughout with the n, we write it as y bar is equal to beta 1 hat plus beta 2 hat x bar. And as we have written earlier, beta 1 hat is equal to y bar minus beta 2 hat x bar. Beta 2 hat x bar. Now, substitute the value of beta 1 hat. the value of beta 1 hat in the second equation. That will give us sigma yi xi summum y bar minus beta 2 hat x bar into sigma xi plus beta 2 hat sigma xi square. Beta 2 hat sigma xi square. Now, expanding this equal to y bar into sigma xi minus beta 2 hat x bar into sigma xi plus beta 2 hat sigma xi square. Sigma yi xi sum. Now, sigma yi xi summum y bar into sigma xi minus beta 2 hat x bar into sigma xi plus beta 2 hat sigma xi square. This can be written as y bar into sigma xi plus beta 2 hat is taken as common. Beta 2 hat, sorry, one more step. Sigma yi xi is equal to minus y bar into sigma xi summum. When these terms are taken to the other side, it becomes minus become positive and positive become negative. Beta 2 hat into x bar into sigma xi minus sigma xi square. Now, this term becomes negative. So sigma xi square minus beta, this term becomes positive and this term becomes negative, this becomes positive, minus x bar into sigma xi. This term is taken to the left, minus, this goes to the other side, this minus becomes plus, this minus beta 2 hat x bar into sigma xi as such, then this becomes plus as such, no, because this part is remaining there. Now, what is beta 2 hat? Beta 2 hat is equal to sigma yi xi minus y bar into sigma xi divided by sigma xi square minus x bar into sigma xi. And as I told you, this is one expression for the expansion, sigma x minus x bar into y minus y bar. And this is one expression for the expansion, sigma x minus x bar square. So naturally, this becomes sigma x minus x bar into yi minus y bar divided by sigma xi minus x bar square. And beta 1 hat is y bar minus beta 2 hat x bar. We can derive these equations simply if we are considering only a two-variable model with two equations in two unknowns. But when we go beyond the two-variable model, we will have for a three-variable model we will have three derivative equations, and solution will be more difficult. So as a general principle, we always use the Cramer's rule. This method can also be used for the solution. Now, as I told you in the beginning, Euler's estimators are obtained by applying the first order condition for minimum. That is, sigma u hat I square is differentiated with respect to beta 1 hat and beta 2 hat, equated these derivatives to 0. Two normal equations are derived. Solving these normal equations simultaneously, we have beta 1 hat and beta 2 hat. Beta 1 hat and beta 2 hat. But this is only a first order condition for minimum. There is also a second order condition. For maxima or minima, second order conditions must also be satisfied. First order condition for maxima and also minima is first derivative equal to 0. The second order conditions must also be satisfied to ensure that this is in fact a minimum or a maximum, as we say. Now, to derive the second order conditions, we have to use the Hessian matrix. If the Hessian matrix is positive definite, then the first order condition, the second order condition for minima is satisfied. If the Hessian matrix is positive definite, then we say that the second order condition for minima is satisfied. And Hessian matrix is formulated by taking the second derivatives and also the second derivatives and also the cross partial derivatives. Let us see how we actually take and form the Hessian matrix. This is not very important, but for your understanding only. Now, as we have derived earlier, dou sigma u hat I square with respect to dou beta 1 hat was written as equal to minus 2 into sigma yi minus beta 1 hat minus beta 2 hat xi equal to 0. Minus 2 into sigma yi minus. This can be expanded as equal to minus 2 into sigma yi plus 2 into n beta 1 hat plus 2 into beta 2 hat sigma xi. Minus 2 into sigma yi plus 2n beta 1 hat plus 2 beta 2 hat sigma xi. And dou sigma u hat I square with respect to dou beta 2 hat is equal to minus 2 into sigma yi minus beta 1 hat minus beta 2 hat xi into xi equal to 0, as we have derived earlier. Expanding this, we will get minus 2 into sigma yi xi plus 2 into beta 1 hat sigma xi plus 2 into beta 2 hat sigma xi square. 2 into beta 2 hat sigma xi square. Now, if you take the second partial derivative, that is dou square sigma u hat I square with respect to dou beta 1 hat square. The quantity is beta 1 hat is equal to 2n. From this 2n. Similarly, dou square sigma u hat I square with respect to dou beta 2 hat square is equal to 2 sigma xi square. 2 sigma xi square. Then the cos partial derivatives dou square sigma u hat I square with respect to dou beta 1 hat dou beta 2 hat is equal to, and the cos partial derivatives are same using the Young's theorem, is equal to 2 into sigma xi with respect to beta 2 hat, 2 into sigma xi with respect to beta 1 hat, 2 into sigma xi. Now we form the Hessian matrix of the second partial derivatives and also the cos partial derivative. Hessian matrix like this: 2n, then sigma xi, 2 into sigma xi, 2 into sigma xi, and 2 into sigma xi square. 2 into sigma xi square. 2n, 2 into sigma xi, 2 sigma xi, 2 sigma xi square. This is known as the Hessian matrix. Then the second order condition for minima is that this matrix is positive definite. The two conditions to ensure that this matrix is positive definite is that 1, n is 2n greater than 0 or n is greater than 0. N is greater than 0. The second is the determinant of the matrix is greater than 0. That will give us 2 in 4 n into sigma xi square minus sigma xi the whole square is greater than 0. The determinant greater than 0. That will give us n into sigma xi square minus sigma xi the whole square greater than 0. Greater than 0. N into sigma xi square minus sigma xi the whole square greater than 0. Now we know that the expansion of sigma xi minus x bar square is equal to, the expansion of sigma xi minus x bar square is equal to n into sigma xi square minus sigma xi the whole square by n. So this condition boils down to sigma xi minus x bar square greater than 0. That is, this will not be 0 if the numerator is not equal to 0. So the second condition, sigma xi minus x bar square is greater than 0. Now let me say what are these two conditions. As you can see, n is the sample size. So the second order condition, the first second order condition is that sample size must be greater than 0. Without a sample, we cannot estimate anything. The second is sigma xi minus x bar square is greater than 0. Remember this, sigma x minus x bar square is equal to 0 if all the x values are equal to x bar. That means if there is no variability in x. If there is no variability in x. But so the second requirement is that there will be some variability in x. These are the second order conditions for minima. Remember this, n greater than 0, n greater than 0, the second sigma xi minus x bar square greater than 0. That is, there will be sample size not equal to 0. Second is there will be variability in x. These are the second order conditions for minima. Second order conditions for minima. These two conditions must be will be automatically satisfied. As an example to this, if there is no sample, there is no estimation. We cannot think about estimation. The second condition can be explained like this. We know that there is variation in y. And suppose that x is remaining as a constant, say xi. So if x is remaining as a constant, x cannot explain variation in y. It's natural. If price is remaining constant and quantity demanded is increasing or decreasing, then the change in quantity demanded is not due to change in price. So there will be variability in price if price is an explanatory variable. Similarly, if income is remaining constant and if consumption is changing from family to family, then it is natural that income is not the determinant of consumption. So income cannot explain variation in consumption. So income can explain variation in consumption if and only if there is some variation in income. These are the second order conditions. So we have derived the normal equations. Solution of the normal equations has given us OLS estimators beta 1 hat and beta 2 hat. We have exposed this in terms of original observations on x and y. We have also derived this in terms of deviations from x and y. And we have considered the second order conditions also for a minima n greater than 0, sigma x minus x bar square greater than 0.